Alright, so in this unit, we are going to talk about bond polarity just a little bit. So we've been talking about ionic bonding, we've been talking about covalent bonding, but when we're talking about the bonds being polar, we're actually talking about usually covalent bonding. So covalent bonding again means that electrons are shared, however, they are not always shared equally. So it's kind of like a game of tug of war between the two different atoms. In equal sharing, such as a diatomic molecule, which again is hydrogen, nitrogen, oxygen, remember there's 7 of them, they make a 7 on the periodic table, they share the electrons equally because they are the same atom, they have the same strength, they have the same electronegativity. Electronegativity, again, is the ability to attract an electron to yourself. So if we're dealing with a diatomic molecule, oxygen, each oxygen is identical, so they're going to pull the same, so in a game of tug of war, nobody is going to win. However, if we're talking about maybe hydrogen and chlorine, if they make a covalent bond, chlorine has a higher electronegativity than hydrogen does, therefore chlorine is going to have a stronger pull, it's going to win a game of tug of war, and so the electrons are going to be around chlorine more of the time than they are around hydrogen. So yes, the electrons are still being shared, but they are not being shared evenly. It's kind of like if mom says share this candy bar with your little brother or sister, and you split it in half, but it's not really in half, and you give them the smaller piece, you're not sharing equally. Okay. So the more electronegative atom will have a stronger attraction and will acquire a slightly negative charge. If it is in control of the electrons more of the time, it will become a slight negative. It's not going to be charged like an ion because it's not actually gaining that electron. It's just around that atom more often, so that atom is going to have a slight negative charge but still not an ion. Okay? This is called a polar covalent bond, or you can just simply say a polar bond. Polar means it has a slight charge. We're dealing with covalent bonding, so polar bond means a bond with a little bit of a charge. All right. So just to refresh our memory, what is electronegativity? It is the ability of an atom to attract an electron. In a molecule, it is the ability to attract a shared electron to itself. An electronegativity of 4 is the highest, and again, if you guys remember from back when we did our periodic trends, fluorine has the biggest electronegativity, okay, and it has an electronegativity of 4, and if you remember, electronegativity gets bigger as you move to the right, and it gets bigger as you move up. That was the trend for electronegativity. So F is going to have the biggest, whereas francium is going to have the smallest, or in other words, if francium for some reason makes a covalent bond, which it won't because it's a metal, it's going to do an ionic bond, its electron is going to be shared very unequally. But let's look at something that would make a covalent bond. So let's compare maybe nitrogen and fluorine. Nitrogen has an electronegativity of 3. Fluorine has an electronegativity of 4. So if these guys were to make a covalent bond, fluorine would be unequally sharing nitrogen's electrons because it has a higher electronegativity than nitrogen does. So therefore, in a game of tug of war, fluorine is going to win. Alright, so when you do these, so now we're going to do just a little bit of math. So when you're doing electronegativity differences and bond types, basically if you do the math between the electronegativity, so like we just did nitrogen and fluorine, if I would have done 4 minus 3, I would have gotten 1. So let's do this. 4 minus 3. This was fluorine, and this was nitrogen. This would give me a difference of 1. So if I look up here, it kind of falls into 2 categories. This type of bond is going to be moderately polar covalent to very polar covalent. But basically, the important part is this is going to be a polar bond. Okay? And if you notice, the bigger the difference is, the more likely it is to be ionic, because if the difference is greater than 2, we're not going to be sharing at all. That one element is just going to completely steal that electron, and it is going to become ionic bonding. Alright, so let's talk about a specific case. Let's look at HCl. A hydrogen has electronegativity of 2.1. Chlorine has electronegativity of 3. So, is the bond polar? Well, if we do 3 minus 2.1, we get a difference of 0.9. Okay, so if we look that up on the chart that we were just looking at, it would put us in the polar range. So we know that the bond is polar. And the chlorine is going to acquire a slight negative charge, and the hydrogen is going to acquire a slight positive charge. Right? So, just to refresh your memory on how to draw this, hydrogen gets 1 dot because it has 1 valence electron. Chlorine gets 7 dots because he has 7 valence electrons. Okay? Hydrogen needs 1 more, chlorine needs 1 more, so we need a covalent bond. So right there, this pair of electrons that we just connected is going to be shared between the two. However, chlorine is going to have a higher electronegativity than hydrogen is, which means he is going to unequally share, which means this end is going to have a slight negative charge, and that's how it's a Greek letter. And then this is going to have a slight positive charge, and that's how you write that one end is slightly negative and one end is slightly positive, because again, these are not ions, so we cannot give them a full charge. They just kind of have a little bit of a charge. Okay, there's actually another way that you can draw this if you don't want to use the Greek letters. You can just do a plus sign. So hydrogen has a slight positive charge, so I do a plus sign over here, and then you just continue that and make it an arrow pointing in the direction of the unequal sharing. So this is telling me that the hydrogen end is positively charged and the chlorine end has a slight negative charge. Alright, so there's another picture of the second way that I showed you. Again, the arrow points to the more electronegative atom. And electronegativity can also indicate the type of bond that tends to form. Again, we can do the math, we can subtract the two numbers, and we can use that chart. We're going to do some practice here in just a minute. Okay, so a polar bond tends to make the entire molecule polar. Not always, but usually if there's a polar bond, the entire molecule is polar. Okay, this is because there are areas of difference. HCl has polar bonds, therefore HCl is also a polar molecule. A molecule that has 2 poles is called a dipole, kind of like HCl. Again, there was a positive end, there was a negative end. Di means 2, so dipole means that it's a molecule that has 2 poles, and 2 poles means it has 2 ends that have a charge. Okay, the effect of the polar bond on the polarity of the entire molecule depends on the molecule's shape. Now, we're really not going to go too in-depth into the molecule shape, but we're going to talk about water a little bit here in just a minute because it has an unusual shape. Okay, carbon dioxide has 2 polar bonds. However, they cancel out. Therefore, it is a non-polar molecule, and we're going to draw it out here in just a second so you can see what I'm talking about. Okay, so let's draw carbon dioxide. So carbon has 4 electrons because he's in the 4th column, so we're going to draw 4 dots. Okay, oxygen has 6, so we're going to draw 6 dots. We need another oxygen. He again is going to have 6 dots because he's in the 6th column. We're going to make 2 covalent bonds between each. So we have 2 double bonds. Now, these are going to be polar bonds because there is a difference in electronegativity between oxygen and carbon. Who has the higher electronegativity? Well, that would be oxygen. He's closer to fluorine than carbon is. So I'm going to draw my arrows pointing in the direction of higher electronegativity. So oxygen is going to have a higher electronegativity than carbon. And over here, again, oxygen is going to have a higher electronegativity than carbon. Now, all of these bonds are polar bonds. However, this is a non-polar molecule because if you look, all the bonds are identical. So yes, in this direction, we have a polar bond. And yes, in this direction, we have a polar bond. But the bonds are equally polar, so therefore, they're going to cancel each other out. So as a whole, this is going to be a non-polar molecule, even though the bonds themselves are polar. Okay, so let's talk about water just a little bit. Water has two polar bonds and a bent shape. How the highly electronegative oxygen pulls the electrons away from hydrogen, and it is very polar. However, based on the example I just gave you, they would cancel each other out. But water actually has a different shape. It has a bent shape, as you can see right here. The last one that I drew out for you, we drew it straight across. But because oxygen has those two lone pairs, remember oxygen has 6, so when I drew him like this. So when he makes a bond with hydrogen and another bond with hydrogen to make water, we have these two guys right here. And these two lone pairs kind of push the bonds down, giving us this bent shape that you see in the picture. Okay? Therefore, it is polar because those bonds are no longer straight across, because they can no longer cancel each other out. Yes, we have a polar bond right here, and yes, we have a polar bond right here, and yes, the bonds are the exact same because it's a bond between oxygen and hydrogen and another bond between oxygen and hydrogen, so the electronegativity should be the same. But it's kind of like in geometry. These things are not going to cancel each other out because they're not working in opposite directions. So that's going to give this oxygen a slight negative charge, and each one of these hydrogens a slight positive charge. So therefore, water is polar, which is what makes water dissolve things so well. Alright, so let's do a little bit of practice now. So, identify the bonds between atoms of each pair of elements as nonpolar covalent, moderately polar covalent, very polar covalent, or ionic. So, we are going to exit out of presentation mode, hopefully, so that we can see our periodic table with the values over here. So let's see here. Hydrogen has a electronegativity of 2.1. Bromine has an electronegativity of maybe 2.8. So if I do the difference between 2.1 and 2.8, I get a difference of 0.7. So then I look this up on the chart. Difference of 0.7 fits in right here. So the bond between hydrogen and bromine is moderately polar covalent. So for the most part, this bond is going to be a polar bond. Okay. Let's look at the next one. Okay, potassium and chlorine. Potassium, we really don't need to do the math on this one, but potassium is 0.8. Chlorine is 3.0. Alright, so the difference between 0.8 and 3.0 is 2.2. So if we come over here and we look it up on the chart, greater than 2 gives you ionic. Now we really didn't need to do the math on that one because we should remember the definition of ionic and covalent bonds. As soon as you saw potassium there, you shouldn't have even had to do the math because metals can only make ionic bonds. Metals do not make covalent bonds. So we should have been able to do that anyone, but the math proves that we were correct. Alright, so let's look at the next example. Carbon has an electronegativity of 2.5. Oxygen has electronegativity of 3.5, so the difference between that is 1. So again, that's going to give us a moderately polar to very polar covalent bond. So in general, again, a polar bond. Let's look at the next one. Chlorine and fluorine. Fluorine is 4.0. Chlorine is 3.0. That gives us a difference of, again, 1, which again is going to give us a polar covalent bond. Alright, the next one, lithium and oxygen, we don't even need to do the math here. Lithium is a metal, so automatically that should tell us that this is an ionic bond, but let's double check. Lithium is 1, oxygen is 3.5, which gives us a difference of 2.5, so yes, ionic, we were right. And bromine and bromine. Well, you don't need to do the math on this one either because bromine and bromine would make a diatomic molecule. They're going to have the exact same electronegativity. So if you do 2.8 minus 2.8, you get a 0, which means it is going to be a nonpolar covalent bond. Alright, so let's do a little bit more practice. Please place the following covalent bonds in order from least to most polar. So in order to do this, I'm going to find the differences really quick because then that'll tell us how polar my bond is. The bigger the difference, the more polar the bond is, and then we're going to put them in order. So to go from hydrogen to chlorine, chlorine is 3, hydrogen is 2.1, so this gives us a difference of 0.9. Sulfur is 2.5. Hydrogen again is 2.1, so this gives us a difference of 0.4. Bromine is 2.8. Hydrogen is still 2.1, so this gives us a difference of 0.7. And carbon is 2.5, and hydrogen is still 2.1, which gives us a difference of 0.3. Remember, again, the bigger the difference, the more polar the bond. So now we're just going to put them in order from least to most polar. So the smallest difference is down here with hydrogen to carbon. This is going to be my least polar. Then from that we have hydrogen to sulfur with a difference of 0.4. That's going to be the second one. After that we're going to do the 0.7, so there's my third. And then the most polar bond is hydrogen to chlorine with a difference of 0.9. So we're going to put him last from least to most polar. You guys have a few practice problems that you need to do. They are on my website in the homework section on the right side of the screen. Please have those completed and ready to go over in class tomorrow.